Hello students, today we're going to learn how to draw more Lewis structures, and there's going to be new rules because there's exceptions to the rules and they're more complex Lewis structures for molecules, that is. All right students, here's two warm-up molecules that you might already know how to draw, but we're going to follow these semi-new rules so that you know how to draw the more complex ones. So we're going to start by following the rules for these easier ones, and then we'll do the more complex ones. Same rules apply. All atoms want 8 valence electrons, and hydrogen wants 2 valence electrons. Remember, carbon goes in the middle. Refer to your old rules, but we're going to follow these instructions. So number 1, count the number of valence electrons. 2, draw the skeleton. I'll show you what that is in a moment. And 3, subtract the bonded electrons. And 4, distribute the leftover electrons. And how you're going to distribute them is to the outside atom first. This is the outside atoms first, and then the inside, or you can call this, we've called this the central atom. Okay, so let's follow the instructions here. So number 1, count the number of valence electrons. As a review, hydrogen has, we're looking at H2O right here, and hydrogen has 1 valence electron because it's the first box in the first row of the periodic table. Oxygen has 6 valence electrons because it's the 6th box from the left in the second row on the periodic table, and we only count the electrons that are in the outermost shell, meaning the highest row on the periodic table. So for oxygen, if you count from left to right, it's 1, 2, 3, 4, 5, 6. So we can say hydrogen has 1 valence electron, but there's 2 of them, so hydrogen brings in 2 valence electrons. For oxygen, there are 6 valence electrons. There's only 1 oxygen in the water molecule. So we multiply that by 1. That's what this is right here. Multiply by 1. That's 6 valence electrons. Add them up. That's a total of 8 valence electrons that we need to account for. That means exactly 8, no more, no less, electrons need to be shown in the Lewis structure. So step number 2, that was step number 1. We just counted them, the valence electrons. Step number 2 is draw the skeleton. Skeleton is super easy. You just draw the hydrogens on the outside, and I'm going to draw the hydrogens on the outside like this. And the skeleton just says to connect them with single bonds. So, and that's the skeleton right there. So that would be step number 2. So we could add connect atoms with a single bond. Okay, that's step number 2. Then it says subtract the bonded electrons. So step number 3, how many electrons are bonded? Well, each line represents 2 shared electrons. So that's a total of 4. So we're subtracting away 4 valence electrons, and we're left with 4 valence electrons that we have to draw. So now we're at step number 4. Distribute the leftover electrons outside first, then inside. So outside, are we going to distribute them to the hydrogens? Well, no, because hydrogen only wants to share 2 valence electrons. So we're not going to distribute them to hydrogens. So the hydrogens are done. Where are we going to distribute the 4 valence electrons? Well, oxygen has 1, 2, 3, 4, and oxygen wants to have 8 valence electrons. Remember, oxygen wants to have 8 valence electrons so that it could gain just 2 more valence electrons, so it has the number of valence electrons as its closest noble gas, so it reaches stability. Okay, so where are we going to put these 4 electrons? We're going to draw them as dots around the oxygen. And you always draw them in pairs. You don't draw them all wildly and crazy. So this would be the answer to there. Let's do a little highlighting. Okay, so you could see the hydrogen has those 2. I should have drawn circles instead of lines, but it's okay. And then now the oxygen has a total of 8. All right, the next example, let's follow the rules right from step number 1. Here's step number 1. Count the number of valence electrons. Nitrogen has a total of 5 valence electrons. Let's review why. Here's nitrogen on the periodic table. It's in the second row, and it has electrons on the first row and the second row. but it only has 1, 2, 3, 4, 5 electrons on the second row, meaning there's 5 electrons in the outermost shell. So that's why nitrogen brings in 5. We know hydrogen brings in 1 valence electron, but there are 3 total hydrogens, so we need to multiply that by 3, and we forgot to multiply that nitrogen by 5. So nitrogen brings in 5, hydrogen brings in 3, and we have a total of 8 that we need to draw. So how does it look? We know the hydrogens go on the outside. That was a rule from a previous video. So let's put the hydrogens on the outside. There's 3 of them. Let's put that nitrogen in the middle. Okay. Step number 2 is draw the skeleton. That just means connect the atoms with a single bond. So boom, connect all of them. Okay, subtract the bonded electrons. How many electrons did we just draw? Well, each bond is each bond is 2 shared electrons. That's 2, 4, 6 electrons that were used up. So we have to subtract away 6 electrons from our total. We have 2 electrons to draw. And where are we going to draw them? Distribute the leftover electrons outside first and then the inside, the central atom. Well, are we going to distribute them on these 2 electrons on the outside to the hydrogen? No, because each hydrogen already has 2 valence electrons, and that's the rule for hydrogen. Hydrogen gets to share 2 valence electrons. So where are we going to put those last 2? Well, currently at the moment, this nitrogen in the middle currently has 6 valence electrons. That's no good because we know that nitrogen wants to have 8, just like its closest noble gas. There's 5, 6, 7, 8. From the left, 1, 2, 3, 4, 5. That was nitrogen. It wants to gain 1, 2. It wants to share 1, 2, 3 more for a total of 8. Okay, so where are we going to put those last 2 valence electrons? Right here in the middle. Boom, boom. Now we've used up all of the electrons, and the nitrogen now has 8. Good job, everybody. You're doing great. We're going to get into more difficult examples. All right, so same rules apply, but it's a different example. So we know that we need to count the number of valence electrons. Carbon has 4 valence electrons. There's only one of those, so carbon brings in 4. Fluorine, there's 7 valence electrons. Let's review again. Here's fluorine way over here on the left side. Fluorine is in the second row of the periodic table. You just count from left to right. 1, 2, 3, 4, 5, 6, 7. Fluorine has a total of 7 valence electrons. Those are the electrons in the outermost shell only. Okay? So 7 valence electrons. There's 4 of them. That means this fluorine is going to bring in 28 valence electrons. And how many is that total? That's a total of 32 valence electrons that we need to account for. That's first step. Step number 1 is done. Step number 2 is draw the skeleton. Remember, that means just to connect the atoms with a single bond. Carbon's going to go in the middle. That's one of our rules. So here's carbon, and we'll put the fluorides on the outside. The more electronegative atoms will be on the outside of the molecule. They'll be physically located on the outside of the molecule. Okay, so let's connect them with single bonds. As a review, the more electronegative atoms are the ones that are further up and further to the right on the periodic table. That's the pattern or trend for electronegativity. Remember, electronegativity just means an atom's ability to hold onto electrons or to attract electrons to itself. This is with the exception of the noble gases. The noble gases don't count for electronegativity. Okay, let's get back to here. How many electrons did we just draw? We just drew 2, 4, 6, 8. So let's subtract 8. And how many do we have left over that we need to draw? Hold on a second. I feel like I'm scrunched up right here. Okay, so 32 valence electrons minus the 8 that we just drew is how many? 24. Wow, subtraction. Okay, so we have to draw the 24 valence electrons. Well, where are we going to draw them? Remember, we're going to distribute the leftover electrons on the outside and then the inside. Well, each of these fluorines is already sharing 2, which means each of these fluorines needs a total of 6 more electrons. So each fluorine must have 6 electrons in order to be obeying the octet rule. And see how I'm drawing them? In pairs on the top, right, left, and bottom. Okay, so how many electrons did I just draw? There's 6, 12, 18, and 24. So I just used all of my electrons. That's it. That's the Lewis structure for that molecule. Okay, more rules. Here they are. We got there. So everybody write this down. These are the exceptions. The exceptions to the rules. They're new rules. Okay, write those down. The bigger atoms can hold more than 8 valence electrons. So P for phosphorus can hold 8 or 10 electrons. It can hold 8 or 10, doesn't have to. Sulfur and bromine, sulfur S and bromine Br can hold 8, 10, or 12 valence electrons. Boron, B for boron, can hold 6 or 8 valence electrons. So there they are. You're going to have to pay attention to those rules when you're drawing the Lewis structure. So let's get going. Let's start talking about it. Okay. We're just going to do this example right now. PCl5. Okay. So count the number of valence electrons. Phosphorus has 5 valence electrons. There's only one phosphorus in the molecule, so that means there's 5 valence electrons for phosphorus. Cl, not Ci, has 7 valence electrons. Find it on the periodic table, and you'll know. And there's 5 total, so that's a total of 35 valence electrons that PCl brings to the molecule. That's a total of 40 valence electrons that we need to account for. Okay, the more electronegative atom goes on the outside. So how do we know which one goes on the outside, which one goes on the inside? Well, you may just know a trend that usually the first molecule written goes on the inside, and the ones over here go on the outside. But the real rule is that the more electronegative atoms go on the outside. And so hopefully you can find phosphorus and chlorine on the periodic table, and you can answer that chlorine is the more electronegative atom because it's further right on the periodic table. So chlorine is more electronegative than phosphorus, meaning chlorine is going to go on the outside of the molecule, and phosphorus will be the central atom. So here's phosphorus in the middle, and we have 5 chlorines. 1, 2, 3, 4, 5. Okay, and we're going to draw the skeleton structure, meaning just draw single bonds between all the atoms. So there's the single bond right there. Okay, and how many electrons did I just draw? 2, 4, 6, 8, 10. I just drew 10 electrons around phosphorus. Well, here's our exception to the rule, to the octet rule. Phosphorus can hold 8 or 10 valence electrons. So we're obeying the rules still, the exceptions to the rules. Okay, we just drew 10. So we need to subtract away 10 electrons, and that's going to be 30 valence electrons left over. And where are we going to draw them? We're first going to distribute the leftover electrons on the outside, then the inside. Well, each chlorine is only sharing 2, so we know that each chlorine needs to have a total of 8. So each chlorine needs to have 6 dots around it, and then each chlorine will have 8. So we know that has to be true. And look where I'm drawing. I'm just on the top. Okay, top left, right, or bottom in pairs. And you can see that each chlorine, if you count the shared electrons in the middle, each chlorine now has 8, and that's good. I don't need to circle the rest of them in pink. You can see that each chlorine has 8 now. And we drew how many electrons? Well, each chlorine, we just drew 6 electrons, and there's 1, 2, 3, 4, 5 chlorines. So that's all 30 of them. So we're done. We just finished. There's 0 electrons left to draw. Okay, that's how you do that molecule. Okay, make sure you write this down up here. Okay, rules for drawing Lewis dot structures. Okay, we're going to be doing more examples. So S for sulfur. Remember, sulfur can hold 8, 10, or 12 valence electrons. 8, 10, or 12 valence electrons. So sulfur brings in 6 valence electrons. There's one of them. So that means there's 6 valence electrons for sulfur. Oxygen brings in 6 valence electrons as well. And there's 3 of those, so that's a total of 18. If we add them together, that's a total of 24 valence electrons that we need to account for when drawing this Lewis structure. The more electronegative atom is the oxygen because it's higher up on the periodic table than sulfur is. Right here, see, there's oxygen, there's sulfur, oxygen, sulfur. So oxygen is further up, meaning it's more electronegative. So the sulfur goes in the middle, and the oxygens go on the outside. Okay, step number 2 is to draw the skeleton. So just draw single bonds between the atoms. That was a bad line. Okay. Okay, so we just drew 2, 4, 6 valence electrons. So we subtract away 6 valence electrons, where we have a total of 18 valence electrons that we need to account for. Where are we going to draw the 18? Well, we're going to distribute the leftover electrons outside first and then inside. So each oxygen needs 6 because each oxygen is just sharing 2 so far. So there's 2, 4, 6. Now this oxygen has a total of 8. Now the oxygen is obeying the octet rule. This oxygen needs a total of 8 as well. So we added 6. That's a total of 8. Okay, now each oxygen, you can see, has 8 valence electrons. Okay, so now the thing we have to look at is the sulfur. The sulfur has 6 valence electrons. But before we talk about the sulfur, let's make sure we analyze our total valence electrons. We drew 18 because we drew an extra 6 for each oxygen. There's 3 oxygens. So we drew 18 electrons. Now we have 0. So that's all the electrons that we could draw. We can't draw any more or any less. Now let's talk about the sulfur. The sulfur in the middle has 6 valence electrons, but that's okay because remember from the rules that we just wrote down, sulfur and bromine can hold 8, 10, or 12 electrons. Wait a second. Sulfur's not the one that could hold 6. That was boron. Uh-oh. So this is wrong then. So what do we have to do? Well, we can use a double bond. This is the skill that you need to have, is that you need to know when you can draw a double bond. So if you notice, all of these bonds in the middle are single bonds. So what I need to do is take a pair of electrons from, like, say, this oxygen up on the top, erase them, but then I have to make sure I draw 2 more, right? So I'll draw a double bond just like that. Now the sulfur in the middle has 8 valence electrons. Okay? Has 8 valence electrons in the middle, in the pink circle. 2, 4, 6, 8. All right, but look what it says. It says sulfur can hold 8, 10, or 12 valence electrons. So there's actually multiple answers to this problem. You can take this oxygen right here, erase 2 of those paired electrons, and make another double bond. This is also the correct answer. Okay, because each oxygen still has 8 valence electrons, and now the sulfur has 10 valence electrons. So remember, the sulfur could have 8 valence electrons, 10 valence electrons, or 12 valence electrons. So what do you think the next thing, another answer could be? Well, we could take these oxygens right here, these electrons from this oxygen right here and make another double bond. So now I've shown you that sulfur could have 8 valence electrons, 10 valence electrons, or 12 valence electrons like it does right now. All of those would be correct examples. Okay? But remember, the oxygens on the outside, they have to have 8 valence electrons. Okay, next example, BH3. Let's follow the instructions, count the number of valence electrons. Boron, find it on the periodic table, has 3 valence electrons. Multiply by 1, you get a total of 3. You should be able to do some of this on your own by now. Hydrogen has 1 valence electron, and there's 3 of them, so that brings in a total of 3. Add them up, there's 6 valence electrons. Automatically, I know that the hydrogens go on the outside. Oops. Hydrogens are going to go on the outside. I'm going to draw it like this, like a triangle type situation. Okay, step number 2 is to draw the skeleton, which means just draw single bonds between all the atoms involved in the molecule. And how many electrons did I just draw? 2, 4, 6. Well, I only had 6 to draw. So subtract away 6, I'm done. That's it. That's the whole thing. Well, wait a second, Mr. Edwards. The hydrogens have 2. That's good. So all the hydrogens just need 2. But the boron can hold 6 or 8 valence electrons. So we're going to show you that this boron right here in the middle only has 6, and that's okay because boron is one of those exceptions to the rule. So that's it. That's all we could do. That's the molecule. Okay, let's do a difficult one there. Okay, we got H2SO4. So remember, hydrogens only need 2 valence electrons to be stable. And hydrogens always go on the outside of the molecule when you draw it. Sulfur could have 8, 10, or 12 valence electrons. And oxygen must have 8 valence electrons. And the more electronegative atoms go on the outside, we already established that oxygen is more electronegative than sulfur, meaning that sulfur is going to be our more central atom, then oxygen's outside of sulfur, and then the hydrogens automatically go on the farthest outside spots. So let me show you how to draw it. But first, let's follow all of our rules. Hydrogen brings in 1 valence electron. There's 2 of them, so that's 2 for hydrogen. Sulfur brings in 6 valence electrons, and there's only 1 sulfur in this molecule, just because there's no little subscript number next to sulfur. And that means there's 6 for sulfur. Oxygen brings in 6 valence electrons as well, but there's 4 of those, so oxygen brings in a total of 24 valence electrons. So all of this added together is going to be 32 valence electrons that we have to account for when we're drawing the Lewis structure. Okay, next step is to draw the skeleton. So how are you going to set this up? Well, hydrogens go on the outside. Boom. Hydrogens go way on the outside. Then the oxygens, and then the sulfur is in the middle. So you kind of see it's kind of like built like this. We have the molecules are set up like this. There's like 2 parts to the molecules. So the hydrogen's there, and then we have the SO4 polyatomic ion in the middle. So sulfur goes right in the middle, and then we have our oxygens around the sulfur. We'll draw it like this. Okay, everybody see? That's the molecule. Okay, now we're going to be just drawing the skeleton structure, which is just drawing single bonds between all of the atoms in the molecule. Okay, now we need to subtract the bonded electrons. That's step number 3. Subtract the bonded electrons. So 2, 4, 6, 8, 10, 12 bonded electrons. So it's minus 12. So that's 20 valence electrons that we need to account for. Well, where are we going to draw these 20 valence electrons? Where are we going to distribute the leftover electrons? Well, we first have to distribute on the outside atoms, then the inside. Well, let's start with hydrogen. Do we need to distribute to hydrogen? No, we don't need to distribute to hydrogen. That's kind of like a pattern because hydrogen just needs the 2 electrons and it is good to go. Oh, I shouldn't have circled that oxygen there. My fault. Okay, and that hydrogen is good to go. So where are we going to distribute them? Let's start distributing them on the oxygen because it looks like oxygen only has 4 at the moment. Everybody see that oxygen is only sharing 4 at the moment? So where are we going to distribute them? Around the oxygens. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I just drew all of them. 20. I just drew all 20 valence electrons right there. So we have 0 left. We're done drawing valence electrons. So on this one, you can see I had to draw extra on these oxygens right here. So that's all the valence electrons that we could draw, and this is the answer to this molecule. This is the Lewis structure for this molecule. What else can you know? Oh yeah, so the sulfur in the middle, remember, it can have 8, 10, or 12. So another answer, another correct answer for this Lewis structure would be if you say like you took these 2 electrons off oxygen and you made a double bond right there. So you see now the sulfur has 10. Now the sulfur in the middle has 10 that it's sharing instead of 8 like it had before. Okay. So yeah, that's how you do more complex Lewis structures. And right here in the middle, the exceptions to the rules, this is really what we learned the most. And follow these steps. They will lead you to the correct Lewis structure answers.